So let's discuss the other fluid properties and let's see some definitions also. So what is density? So density is how much mass I can keep, I can pack in a unit volume. Okay. So basically, as per the definition, so how much mass I can keep in a unit volume. Okay. So in 1 meter cube volume, say if I'm able to keep 5 kg mass, so the density is 5 kg per meter cube. This is how it defined. So similarly, this definition is universal for even for liquid, solid, gas. Okay. So that's the thing. So now if I have a liquid and say something like this, so if I take a unit volume here and measure the mass it occupies in that volume, then the ratio of those two is called as density. Now let's say you have the rho L is the density of liquid, and liquid might be anything: water, benzene, ethanol, and rho W is the density of water, which is normally 1000 kg per meter cube at standard temperature and pressure. Okay, and it doesn't change much. I mean, the density of water doesn't change much unless it changes any state. Okay, so between like from 0 degrees to 100 degrees centigrade at 1 atmosphere condition, it doesn't change much. But ice and all, when it changes the state, about to change the state, density changes. Okay, but at standard temperature and standard pressure, the density of water is 1000 kg. Now this ratio is defined as the specific gravity of a liquid. So specific gravity of a liquid is basically density of the liquid by density, okay, density of the liquid to the density of water. The density of water. So always, I mean, instead of specifying the density, whenever the density of the liquid is given, it's not given in terms of okay, so always this value is given, the specific gravity of liquid is given. Say the specific gravity of mercury is 13.6. So the density of the mercury, which is denoted by rho, is basically 13.6 into density of water, which is 13.6 into 1000. So 13600 is kg per meter cube is the density of mercury. So this is how the definition goes. Now there's another terminology which is commonly used with liquids is specific weight. The specific weight is basically weight per unit volume. Just like density was mass per unit volume, the specific weight is weight per unit volume. Okay, so weight per unit volume. Now weight is always m into g, mass into gravity, which is v. Okay, m g by v. Now m by v is always rho, so rho into g. So specific weight, which is denoted by omega or small w, is basically density of the liquid into g. These are some definitions. So let's see another property of liquid and of a fluid, basically compressibility. So now compressibility is basically how much ease you can compress a fluid. That is what is measured by compressibility. So with in relation to compressibility, we have a parameter which is, or a property of fluid which is denoted, okay, by bulk modulus of compressibility. And let me first give you the definition, then I'll explain what it means. So it is defined like this: the change in pressure in the numerator, whereas and in the denominator the ratio of the change in the volume to the original volume at constant temperature. So what it means is, this parameter, when you evaluate, what it means is or let me just explain this way. So you have, say, you have a sphere on in which you have the liquid. Okay, now say you are applying a uniform pressure. Okay, and this uniform pressure is from 0 to P. Suddenly I have applied. Now how much change in volume you can notice? Okay, so with increase in this compression pressure from 0 to P, how much change in the volume or how much decrease in the volume I can measure? So that ratio is comes under bulk modulus. So larger value of K, what it means? It means larger change in pressure is needed to cause, so large change in pressure is needed to cause small fraction change in volume, small fractional change in volume, change in volume. So that's it. So K value larger means the fluid is incompressible. So incompressible means it is very difficult to compress that fluid, or basically you need a very large amount of force or large amount of effort to compress a given change in, to compress it by a given volume. Okay, so that's it. So larger the K value, the fluid is incompressible. So lower the K value, fluid is more compressible. Okay, so that is what I mean the value tells. For example, if I just state the bulk modulus of water and bulk modulus of air, see bulk modulus of water from the value it comes out to be 2.06 10 power 6, whereas for air it comes out to be 1.03 into 10 power 5 Newton per meter square. So if I take the ratio of K air to the K water, K air roughly, so this is roughly 2 into 10 power 4 or 1 by 20,000. So what it means is K air is 1 by 20,000 of K water. So means that K air is a lower value 1 by 20,000 of K water or bulk modulus of water. It means that air is 20,000 times more compressible than water. So what it means, most of the liquids are generally incompressible because of a larger value of bulk modulus. So here for example we can see the bulk modulus of water is very high. So most of the liquids are incompressible, or it means that the volume change is very less. Even you have a significant change in pressure, the volume change is very less and therefore are incompressible, volume remains constant. So that is what, or I mean you can say that volume, to bring a significant change in volume you require very high pressure. Okay, or in a sense very high pressure also you can bring only a very small change in volume, and mostly the volume change is negligible, whereas gases are compressible. So that's why here in this example you see that air is 20,000 times more compressible water. So that's the physical meaning of bulk modulus. So higher the value of bulk modulus, it means the fluid is more incompressible. That is how it goes. Fluid property. Now we have another property of fluid called coefficient of volume expansion. Okay, which is just defined like this: the change in volume, okay, per unit change in the temperature at constant pressure. So if I change, say, a temperature by delta T, then how much the volume changes? So that is measured by coefficient of volume expansion. So these are some of the properties which we studied. The main property was viscosity, and then we had this compressibility, which is more dominant in gases, and then we measured this coefficient of volume expansion. And apart from these three, we defined some physical terms that are used with fluids, mainly the density and the specific weight and the specific gravity. So that's it. So now let's come to a very important concept in fluid mechanics. What is a pressure? Okay, so in this section and in the corresponding section followed by this, we'll see what is pressure and how it varies with the height, and how to measure atmospheric pressure, and what is manometer and stuff like that. So first of all, what is the pressure in a fluid? So in order to understand this, let's consider a beaker which contains water or some fluid, right? Okay, so now consider a point A in the fluid, and if you imagine a small area, say delta S, this depends on where you take the area. I mean, you can take any along any angle. So if I take the area delta S, something like this, so this is delta S, and this point you can see that is point A. So now the fluid on one side of the area will press the fluid on the other side, and vice versa. That is, I mean, this is what you can imagine. Okay, so fluid on this side will press A, and the fluid on the other side will press A. So now let this common magnitude of the force be F, and the way we define the pressure of the fluid at this point A is in this way. Pressure of the fluid at A is defined as, I mean, this is the mathematical definition. So limit F. So if you just take the ratio of this force, the common magnitude of the force that is exerted by fluid on either side on this section delta S, so F by delta S, and in the limit that delta S be very small, so then this mathematical, I mean, this is the mathematical definition, but the physical meaning is that this magnitude F, when it acts on a very small area delta S, so then this quantity is called as pressure P. And it can be shown that this quantity does not depend on the orientation of delta S. Okay, we can show that mathematically, but not here. When from the proofs and all that, we can show that the orientation of delta S does not matter the value of P. Hence we talk of pressure at a point, we don't say what direction. Hence we talk of pressure at a point and don't tell anything about the direction. Don't tell or don't mention anything about direction, because it is direction independent. So what it means is, if I would have taken at point A, if I would have taken, say, instead of like this, if I would have taken an area like this or like this, whatever section if I take, and find out the force by that area in every, or at this point, say if I have this F by delta S, so if I have the force by delta S, I'll get one pressure value. Or if I say take at this point, similarly if I take area instead of like this, if I take an area like this and find out the value is same. So what I mean to say is that this, so when I say pressure at this point, it means that whatever area I take and in whatever orientation I take, delta S, the value will come out to be same, and hence this value is basically, and this is a scalar. So at a point you have only one value. Okay, so now let's see how it varies with distance or varies with height particularly. Okay, so let us consider a stationary fluid. Okay, let us consider stationary fluid at rest in a beaker, and consider 2 points A and B. So at A, say if I take the area to be delta S, and at B also say I take the same area delta S, and joining these I join the vertical walls. So basically what I have done is I have considered 2 points A and B separated by some vertical distance. Say let's call that is dz is the vertical distance between A and B, and the horizontal area at A which I have taken is ds, and the horizontal area at B is ds. And imagine that you have considered the fluid enclosed in this vertical wall. Okay, so now I have the fluid between A and B, and I am considering it enclosed. Imagine, I mean, it is enclosed by vertical boundary joining A and B. Now this fluid, what are the vertical forces? So let's list down. So at A you have the bottom fluid will be exerting some force, and that is summed as F1. On the top of B you have the fluid, so that would be exerting some force on B, that is F2. And also the weight of the, so what I am doing is basically I am drawing a free body diagram of the fluid that is inside A and B. So I have the bottom fluid will be exerting some force on A, that is F1, the top fluid exerting some fluid on B, that is F2, and now the weight of the fluid that is enclosed in this imaginary cylinder is W. Okay, so now by equilibrium I can say this is the free body diagram of the fluid element or imaginary cylinder, the fluid element enclosed, or the fluid enclosed in imaginary cylinder. Okay, so these definitions should be good. Now because it's, so we can apply all the static equilibrium equation. So I have just considered only the vertical forces here, and so if it is in equilibrium there shouldn't be any unbalanced force in the y direction, so sigma Fy has to be 0. So taking upward forces to be positive and downward to be negative. F1, okay, W is acting downward, so minus, and F2 is acting downward, so 0. So this has to be 0 for vertical balance, so F1 has to be W plus F2. Okay, now how do I express F1 and F2 in terms of pressures? Now we know that going by this definition, pressure here, say if it is uniform, then pressure is basically F1 by the area which is ds, which is very small, so I can say it to be ds. So F1 by ds, okay, that is the pressure, so I can write F1 as P ds. So similarly for, say at this is at A, now at B, say the pressure is P minus dP or P plus dP. Okay, let's say the pressure has increased by dP, so P plus dP is F2, is the total force that is exerted on this section B where the area is ds again. So I can write F2 as P plus dP into ds. Okay, and now what about the weight? The weight is basically mass into G. Mass is basically the density into the volume into G. Now volume density is rho, volume of this cylinder is, well, ds is the area. So imagine, I mean area means here it is, say imagine it's a cylinder, so circular area is ds and dz is the height, so ds into dz is basically the volume into G. Okay, so now keeping all these three, I mean this is 1, say this is 2, and this is 3 in the equilibrium equation. So using 1, 2, 3 in star, what will I get if I use all this? So I'll get F1 as PdS is equal to W as rho ds dz into, so ds dz into G plus F2 as PdP into ds. So from this I can cancel ds throughout. Don't confuse with rho and p symbol. So what I can get is, I can say that dp is, ds cancels throughout, so dp is minus rho g dz. This is what I got. It means that if I go from top from A to B, the pressure has decreased because dp is negative, so it means that pressure has decreased if I move from A to B. So what it means is that as I move from A to B vertically up, dp is negative, hence the pressure decreases as I move up from A to B. So by the amount rho g dz. Okay, so now if I consider, say, so this only, if I consider, say, you have a free surface here, 2 points. So I have considered 2 points, one at, say, this is my z, so this is at z is equal to 0, and this is, say, the free surface, or not the free surface, I mean, say here the pressure is P1 and here free surface or some other point, let's say, let's have a general expression. Okay, so not the free surface, we'll talk about the free surface later, what is the significance and what is the pressure acting at the free surface. So at, say, at some height the pressure is P2, so this is point A, this is point P. So now from this definition I can say I got dp as minus rho g dz. Now if I integrate this, point A being here where the pressure is P1 and the point B the pressure is P2. Similarly at Z, at point P1 the Z is 0 and at point P2 the Z is H. So this I'll get P2 minus P1 as minus rho G H. Okay, if you just integrate this, so P2 is, or in fact P1 is P2 plus rho G H. Or so what it means is, as you move down, pressure increases by amount rho g h. So this is a very important. So the difference in the pressure is basically rho g h. Okay, that's what it means. If I take, now similarly, if I happen to take, say, a level something like this, instead of taking a vertical imaginary cylinder, if I take a level something like that, this is delta S and this is delta S, and this is point A and this is point B. So from this I'll observe that from the same thing, force balance. Okay, imagining, I mean, this, let's say here the fluid to the left of A is exerting a force F1, the fluid to left of B is exerting force F2. So now, but the weight will be acting downwards, right? So for horizontal balance, if I do, I should be getting F1 is equal to F2, but F1 I can write, say, the pressure at point A is P1 into delta S, and pressure at F2 is, say, it has increased by delta P to delta S is the area. So with this I will get that delta P is 0, or there is no change in pressure as I move at in the same height. This, remember, this happens only when you have a static fluid. Okay, so pressure is same at 2 points in the same horizontal level. Okay, so this is an important statement, that at the same horizontal level pressure is same at 2 points, and as you move down the pressure increases by amount rho gh. So these two are very important concepts, okay, when it comes to pressure. Okay, so now let's talk about, now coming to an important topic, which is basically a built up, which can build up based on whatever we have discussed. So atmospheric pressure and barometer, on whatever we have just discussed, and barometer. Okay, so now coming back to thinking in a global sense, so if you have earth like this, so till some distance, if you move upward from the earth's surface, you have the stretch of atmosphere, and it is being said that the atmosphere of the earth is spread up to a height of 200 kilometers. So this height is roughly 200 kilometers. So now imagine that this is the earth's surface and you have atmosphere height of 200 kilometers, and here basically you have the vacuum pressure. Okay, the pressure is vacuum here about the, so this is all air. Okay, so air is like a fluid, and I can just consider that as you move downwards from the vacuum, or from the point at which the atmosphere starts, from there towards the earth's surface, the pressure will increase. That's what we have seen from this formula. So as we move down, the pressure is increasing by delta H. So the force, so in that sense, the force that is exerted by air, the force that is exerted by air on any body is perpendicular to the surface of the body. And the way we define the atmospheric pressure in the same way. So if you consider a small surface delta S, in contact with air, and the orientation doesn't matter as we have seen previously. So the force that is exerted by the air on this part of delta S, the ratio of that, and again the limit tends to 0, so that is called your atmospheric pressure. So atmospheric pressure at the top of the atmosphere, obviously there is a vacuum, so it is 0, and as there is nothing above, because there is nothing above to exert the force, so that's why the atmospheric pressure here it is 0. And as you move down, the pressure increases, that we have seen, and but at the same constant level, at the same horizontal level from the earth's surface, the pressure is same. That is what we have seen previously. Okay, and so if I say the atmospheric pressure at Patna is 76 centimeter of mercury, so I need not specify, or for example let's say say the atmospheric pressure at Bangalore is 76 centimeter of mercury, then I need not specify whether I am measuring it at MG Road or I am measuring it at Majestic. It remains same. Okay, that's why it doesn't matter. Because I mean, unless there is a change in the level, like unless there is a drastic change at the level. So if I imagine that the Majestic as well as the MG Road are at the same level, the pressure is same. Okay, so it matters only with the height. Okay, but how do I measure it? How do I measure the atmospheric pressure? So Torricelli, way back in, I think in 19th century, so Torricelli has devised a very simple instrument to measure the atmospheric pressure, and this instrument is called barometer, and this also works on the same principles whatever we have discussed. So it looks something like this. You have a fluid, okay, so you have a glass tube which is open at one end and having a length of about a meter basically. So it is inverted like this and filled with mercury. Okay, so the open end is temporarily closed by the thumb, or so I mean you can close this open end. Basically this is an open end, you can just close it by thumb or something, or you can just invert a tube